Hello, everybody. Welcome to my Physics 2 Lab 3 report. This report will be on our circuits lab. There is no code for this lab because it is not required. This lab was all done physically. So the purpose of this lab is to use the principles of energy conservation, the loop rule, and current conservation, charge conservation, plus definition of steady state. We were going to predict the behavior of circuits containing resistors in series and parallel. We also use multimeters to measure the actual values of conventional currents and potential differences in circuits, and examine the behavior of ohmic resistors and capacitors. So fundamental physical principles here include charge conservation and energy conservation. We'll be studying voltage, current, resistance, capacitors. Circuits and RC circuits will be used, as well as circuits in series versus circuits in parallel. The system is, of course, the circuit in use, whatever circuit we're studying, or maybe even the light bulb of the circuit, versus surroundings being everything else, like external electric fields that could be messing with our measurements. So this is the model of one of the circuits we're going to be making in lab. And so far, if we look at this model, we predicted that the current for I1 and I2, if you look at the amp meters, would be around 0.024 amps. One thing to know before we continue is that this is how you know a resistor's resistance by the colors on it. So this is how we assembled the correct circuit using the correct resistors. So this is the setup we're going to also be used. It's another version of the setup showing the multimeter in the middle, the batteries, the amp meter, and as well as resistors. So once we built our circuit, we collected data on current 1 and current 2, which were 18.6 and 20.3 amps respectively, which is very different from what we got originally. So the data we got is much higher. So we were totally wrong and theoretical. However, when we reversed the connection, the currents became the first current and the second current became around negative 18.6, which makes sense. If you reverse the way you measure the current, it's going to be negative instead of positive, or this negative of the original answer. So after we converted the amp meters to voltmeters and got from 0 amps to 3.1 volts, we changed the circuit to be in parallel instead of series to get these new actual answers. And then for part 4, we did the potential difference across circuit elements. So for the battery, it was 1.5 volts each, theoretically 1.5 each, but 3 volts in total. 19 amps was the current between these batteries. And for the resistors, 100 ohm resistors had a 2.2 volt measurement, and 47 ohm resistor had a 1.0 volt measurement. For circuits part 5, the sum of the potential differences was around 3.2 volts, theoretically 3.8 volts, because it's the voltage of the two batteries. However, the theoretical is higher because it doesn't take into account internal resistance from the wires. Instead, it only takes resistance from the resistors. This is a graph of the data we got as well. RC circuits are the next up, and really all you need to know is that for an RC circuit, we're looking at how the capacitor charges or discharges. We used this setup to see how capacitor charges discharges by looking how a light bulb lights up and dims. So when we connected the light bulb with the capacitor and the battery, the light bulb light up immediately, but started to slowly fade around 50 seconds. This was because the capacitor was charging up, and the current was going through as the capacitor charged up for 50 seconds. Reversing the thing, so the capacitor discharged, the light bulb light up again, but faded around 50 seconds. This makes sense. It wouldn't change the time because the capacitor would light up and because the capacitor would charge up and discharge at the same amount of time. If we used a light bulb with a higher resistance, we got a much higher time for how slowly the light faded, meaning the capacitor took a much longer time to charge up and discharge, which makes sense because the resistance is super higher. This is the data we got as well to prove our point. Now, what if you had a capacitor with no resistor in the circuit? Well, theoretically, the capacitor with no resistor would charge up instantly and discharge as instantly as well because there's no resistance. However, theoretically, that makes sense, but in reality, it wouldn't because the wires themselves have resistance. So there'd still be some time between the capacitor charging and discharging. And some errors we may have made are the measurements of the circuits. We also may have had some discharging from our fingers if we touch the circuit itself. So those are some wrongs in our data. Thank you.